Hello again, my chemistry people, and we're gonna pick up right where we left off from last time. Half-lives. Actually, we're gonna let half-lives go, man. We're done with half-lives, and today we are gonna talk about nuclear energy, nuclear power, where it comes from, how we do. Really, actually, we're just gonna barely introduce into it. This is some awesome, some crazy complicated stuff, but we are just gonna learn about it as much as we need to know for being chemists and like good citizens of the world. So here's the deal: nuclear energy. There's some trippy stuff that happens in the nucleus, right? So I guess the one thing that's that sort of tripped people up in the very beginning was they noticed that if you take two protons, like over here and over here, right? This proton weighs 1 atomic mass unit. This proton weighs 1 atomic mass unit. They put them into a particle accelerator. They smoosh them together, and their mass is not 2. What? Yeah. So there's this thing with like nuclides, where 1 plus 1 does not actually add up to 2 anymore. So if you take one proton and one proton, you add them up, you get like 1.998, which is really small. But still, it's small enough, it's like big enough for us to measure, and it's definitely not there. Like some of the matter has disappeared. And like, dude, what? Turns out, matter can be converted into energy. Matter is just a form of energy, right? Like ice is a form of steam, I guess you can think of it. I think of it, for as right or wrong as I am, is that matter is like this condensed form of energy. Once you get enough energy, it like snaps into matter. And that's kind of what happens here. And then, but because matter can also be converted into energy. And so when you have two nuclides, like two protons, and they come together to like form a nucleus, a little bit of that matter is converted into energy, or for us, the strong force. You guys remember the strong force, right? When we were talking about nuclear stability, it's this crazy power of attraction that holds positively charged protons together. Well, where does it come from? It comes from matter. Matter is converted into energy, which then holds these things together. So, yeah, that's where nuclear energy comes from, right? So typically what we do is we split atoms into fission. It's a process called fission, and we break the atom apart. And when we do that, a little bit of that matter is converted into energy. Right? And for us, the way we do nuclear energy is that matter is converted into energy, and that energy is used to boil water. I mean, like boil an amazing amount of water. But the steam turns a turbine, and then that spinning turbine makes electricity, just like a windmill, like a wind power. The wind spins a turbine. The spinning turbine makes electricity, and off you go. Well, you want to know how that works? Talk to Schaefer next year in physics, and you will learn how. It takes a little bit to get there. So that's basically how nuclear energy works. Nuclear bombs work very much the same way, only the difference is like in a nuclear bomb, the uranium and the plutonium or whatever we happen to be using, it's an uncontrolled chain reaction. We just let it go, and all that matter gets turned into energy, and we make a parking lot out of a part of our Earth. And nuclear power, the fuel is a little bit diluted, so we can control that nuclear reaction, right? We can control it so that it goes, and at some point we stop it. We stop the nuclear reaction, and then we have all that energy used to make hot water, to make a turbine, to make steam, and blah blah blah, and all that good stuff. So basically, that's it. And then there's fusion, where two atoms are put together. That we don't touch that because we can't, because that's like what the sun uses, and we have yet to be able to make the sun here on Earth in a controlled manner that's not terrible. Yeah. All right, so let's dig into it. So here's the deal: nuclear energy, guys. Is it good or is it evil? Yes. As with all things, it is neither good nor bad. It is how we decide to use it. Can we be responsible enough to use it without wiping out the Earth and making it uninhabitable? By the way, uninhabitable for us. We're the ones who will suffer. All these other places that have terrible nuclear fallout, nature's taken over. It's green and lush, and there's wildlife living there. Can we? No. So it's us. It's us. It's not just about Bambi. But let's dig in. Nuclear energy. So this is the thing that I was talking about. For subatomic particles, matter does not weigh the sum of its separate parts. In other words, when you take separate like protons and neutrons and you add them together, you lose some mass. Because when subatomic particles form nucleus, it's that matter is dude, this is the thing right there. Matter is transformed into energy. Oop, that's a bad boy. That's terrible. Matter is transformed into energy. Matter is transformed into energy. That's the thing about nuclear energy, right? And that matter, what we call that the strong force. Remember we talked about that earlier. That's the force that holds the nucleus together. Unbelievably powerful. Like orders of magnitude stronger than gravity. However, the distance that it's effective is like just the nucleus of an atom, which is unfathomably small. I mean, just so small, which is good because if the strong force extended as far as gravity, we would all be crushed into like our entire planet would probably be crushed into the size of like something smaller than a grain of sand. Like it's just ridiculous. So for nuclear power, right? For us, we're going to look at two things: nuclear power for electricity and nuclear power for, destroying most of humanity. It converts matter into energy. If we do it slow and controlled, we can make electricity. If we let it go uncontrolled, we have a bomb and we have glass instead of habitat. And the strong force. In a nucleus, the strong force is the force that holds a nucleus together. You dig? Awesome. And this is where, that's why this was so significant, man. You guys remember the Manhattan Project? If you don't, you should look that up. That is insane. Einstein came up with this elegant, simple, beautiful equation, E equals mc squared, where what this is saying is the amount of energy contained in mass. This is like the relationship between energy and mass, right? So it is mass times the speed of light squared, and that'll tell you how much energy is contained in a bit of mass or a bit of matter. And to put things into perspective, I read this article and I can't remember the exact, but it was like, how like there's all these comparisons, like analogies, like, okay, if an atom was the size of a football stadium, the nucleus would be a dime, or like a marble. Well, the analogy was the amount of matter that was converted into energy in Hiroshima and Nagasaki was about the mass of a dime, like teeny little bits, just a couple grams. Now it's in the 40s. I mean, think about telephones in the 40s compared to what we have now. Man, the weapons we have now. But that's just to give you an idea of the amount of energy we're talking about. To convert a dime into energy, you make a city go away. That's hard to imagine. At least for me it is. This is like edging on the side of like places where humans are going to get ourselves instantly into trouble. Is it a solution for the carbon thing? I don't know. But there's E equals mc squared. It's where it shows us the relationship between matter and energy. And in nuclear power, we convert matter into energy. Like gobs and gobs and gobs of energy. And so there's only two things that we're going to dig into. We're going to dig into fission and we're going to dig into fusion. And again, the names sometimes indicate what exactly is going on. And sure enough, they do right here. Fission. A fissure, like if you ever go hiking in like it's actually like alpine hiking and mountaineering. A fissure is something you have to be really, really, really careful of, because like if you ever watch movies of people climbing like Mount Everest or Katahdin or anything, they're like poking their sticks ahead of them, because a fissure is where you're walking along and there's this giant fissure or like a crack or a break in the ice. And you have to be really careful because there's snow on top and you can fall like hundreds and hundreds and hundreds of feet down these little fissures, these like breaks or cracks. And a lot of times what they do is they'll take a ladder and they'll lay a ladder across and they crawl across the ladder, and it's craziness, but it's also amazing. Now, fusion, when you fuse things together, right? Like welding, is fusing things together. You take two separate pieces of metal, you take electricity and you melt it, and blah, 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 blah. It fuses the pieces of metal together, right? That's what fusing is. Fusing is smooshing together. Well, that's exactly what it is on an atomic scale. Fission, which is what we typically use, because we can actually control we can control fission here on Earth. We can also make it do what we want. So fission is splitting. It's fissure. It's a split. It's splitting of a large nucleus caused by the collision with a neutron. So basically, we take a big fat nucleus, like a huge nucleus, one that's like just barely holding on, right? It's so big. It's so big that like the nucleons on this side that have the strong force, like the strong force coming out of these things, can't necessarily reach the other side of the nucleus. It's so big, it's like almost outside the range of the strong force. So it's just this huge, unstable thing, just waiting to explode. And wham, we hit it with a neutron, and it just pops in half. It just breaks in half, right? And when that happens, it releases two smaller, almost always radioactive elements. And this is what happened in Chernobyl. This is what happened in 3 Mile Island. I don't know if you guys know about 3 Mile Island. That was when I was a little kid, and it was very, very close to where I grew up. I could look and see like the steam coming out from 3 Mile Island when I was a little kid, and it almost went Chernobyl. Truth. It would have been, well, I wouldn't have been here, that's for sure. Anyway, it's kind of freaky to think about. So what happens in fission, we split a large nucleus into two smaller, usually radioactive elements, and then a bunch of extra neutrons come flying out. And that's the clutch part. There's extra neutrons that go flying out. And we usually use uranium. Why? Well, uranium, we use different like isotopes of uranium, because uranium is like, believe it or not, it's relatively stable. Like, you can have uranium on your desk and it'll just stay there. It doesn't degrade so fast that it just like goes away. Some things degrade, like their half-life is a couple of days. You don't want to have a nuclear power plant where your fuel is only good for a couple of days. So uranium lasts quite a bit of time, which is a blessing and a curse, because it lasts kind of like forever. So it's radioactive, sort of forever, hard to get rid of. However, in a nuclear power plant, if you smack one neutron at a uranium, in this case it's radium-235, the uranium splits in half, very, very predictably, always into a barium and a krypton, right? And 3 neutrons. And like gobs of energy, like gobs and gobs and gobs of like, this is the kind of energy that's like, it's hard to like wrap your brain around. It's an immense amount of energy. But what happens with this is like 3 more come out of the nucleus, or 3 neutrons come out of that split nucleus, and those 3 neutrons split 3 more. And those 3 more spit out 3 more. So we went 1 to 3 to 9 to 27, and this is like, with like, these things are moving like 30% the speed of light. Like, they're going fast. So it's like they propagate almost instantaneously. So, you know, it could be good or bad. It could be good or bad. So here's what's happening. This is like a picture of what's going on inside the nucleus of a nuclear chain reaction. Got it? So here is our original, like, uranium, right? We take a neutron, and we go, bam, when we smash that thing. It's not really much of a smash. The neutron just sort of hits it. It's not even much. It's just, you just throw a neutron at it, and it's so unstable, it just breaks in half. And a barium and a krypton, and look, 1, 2, 3 neutrons come flying out. Now it hits 1, 2, there's a third one in there, but we just don't have space, and then more and more and more, and then just like there's another one and another one and another one. And so what happens is, so if you have like a little block of like uranium, you just need to like zap it right there, and it's like blam, 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 and it just like the entire sample turns into lots and lots of energy. And barium and krypton, which are also radioactive and also cause a problem. These things, that's a little side note, you guys don't actually need to know this for any like test or quiz, but these things, the barium and the krypton, this is what gets people. This is like Well, what also happened in Japan, like remember with the whole tsunami thing wiped out all their powers? They had a power supply, they had a backup power supply. But what got Japan is that they had all these portable generators like to provide electricity for the nuclear power plant to like take care of these things because these are the problem. Because they're still radioactive and there's nothing that stops a nuclear reaction once it go like nothing stops it because everything's on the outside. Everything's outside by the electrons. But what happened in Japan is they had these like portable generators and they went to go plug them in and they didn't match. Like the plugs in the socket didn't match because I think the generators were made in one country and Japan made their nuclear power plant and they didn't quite line up. You know, like if you go to like England, the plugs in England don't match the plugs here. Bummer. So what happens is when a nuclear power plant gets out of hand or gets out of control and has what they call a thermonuclear meltdown, is when these things, the byproducts, right, aren't cooled down. They just go and go and go and go, and they get so hot that well, they call it a bit of an explosion. And we can talk about that in a bit. We have some pictures later on. But this is the new, like, how it happens. And if you have a pure piece of uranium, man, these atoms are right next to each other. So those three neutrons, like this is like right here, it immediately causes three more nuclei to split, and those three, like 27, like instantly, like right away, because then everything's right next to each other. Now in a nuclear power plant where we want to control it, we have uranium, not pure uranium, it's like diluted inside like basically clay, and so it's very dilute. And so we mix uranium into clay, so it's very thin, very sparse, so not all three of the neutrons hit three nuclei right away. It like takes a while, and some of the neutrons just go out into space and don't hit any uranium and don't cause a chain reaction. So an uncontrolled chain reaction results in a nuclear explosion. So when we have uranium next to uranium next to uranium next to uranium, it goes boom like crazy. But a controlled chain reaction is what we use for energy. So if we want to blow something up, we have very pure uranium. So if you listen to what's going on in the Middle East, we have one of our, there's a country out there that hates our guts. What is it, Iran? There's so many right now. But if you listen to what they're talking about, these centrifuges, they use centrifuges, like huge, like massive centrifuges, not like something, not a tabletop, but like industrial sized, to purify uranium. You're right, you want to get one specific isotope and you want to get it super duper pure, and they do it by centrifuging. You can get very pure uranium, and that is what that's where you get this. So there's a lot of stuff going on about preventing some people who don't like us very much, to prevent them from getting these things to make very pure uranium, which makes that. Now, if you don't have pure uranium, if you dilute it, you have this, right? And what we do is you literally get the uranium, you grind it up into a powder, you mix it into clay, like a huge vat of clay, so that the uranium atoms are very far away from one another. So those three neutrons don't necessarily hit all three, so when you split one uranium, three neutrons come out. Those three neutrons don't necessarily split three uraniums. You want most of those three to just go off and do nothing, right, and miss. And how do you do that? By making the uranium spread out and very sparse. And that's what we get with a nuclear reactor. You guys picking up what I'm putting down? Now, fusion. So that's fission. Let's call it with that. Fusion is when we combine things, where we take two little things and we fuse them together. This is what the sun uses. We have not been able to do this in a way on Earth that we can extract energy. But if we could, man, if we could replicate the amount of energy coming out of the sun in a lab, dude, energy crisis over. Like, we're good. Like, we're fine. So this is kind of an issue. You'll hear it's called cold fusion, because right now fusion puts out this much energy, but it requires us to put in more to control it and make it happen in the lab. But what we need to know is that it is combining two light or small nuclei. We are combining two small nuclei. When that happens, Like, over here, fission puts out some energy. Fusion, it's stupid amounts of energy. It's the sun, it's stars, it's the energy of the universe. This is a lot of energy. This puts out way more. We cannot quite control this in a meaningful way yet. We can make it happen, but not in a way that we can extract energy. But if we could, boy, the amount of energy. Imagine having a little teeny sun in your backyard to like charge anything. Whoa, we're done! Really? Is that it? What? That's awesome. Hey guys, I'm gonna click or link or put up a few videos. I want you guys to watch them. See, like, they do a much better job of explaining nuclear power, good or bad, because yes, is it good or is it bad? Yes, but these videos do a great job of sort of capturing that, like, idea of good or bad. But I want you guys to work on this one, right? Yeah, fission or fusion, or fission and fusion. Okay, on the beginning here, there's lots of reading. It explains everything that you're gonna need to know is in the reading part. So, oh my God, I'm gonna insist that you read. Use it, like, do that. Okay, that's it for today, man. That's all I got. I hope today is also yet another really wonderful day as we come speeding toward the end of the year. All right, guys, have an awesome day. I'll see you again tomorrow. I won't see you again, but you'll see me. So I guess that's good enough.